So whilst you're working on that, quick introduction to myself. My name is Bart Delafauer. I work with the OGC, the Open Geospatial Consortium, and I'll be talking today on citizen science and how that relates in the Inspire context and thinking outside of the box. There was a panel there that says think outside of the box. So my last four slides will be thinking outside of the box. So bear with me as I think outside of the box. My specialities within the OGC relate to citizen science, smart cities, linked data, and the world of BIM and GIS. But today, topic, citizen science. Are you all familiar with citizen science and what that means? So that is folks like you and me that go out, make observations, and those observations are then used as additional data for, could be decision making, could be anything else. But emphasize citizen data does not replace any existing data, but is additional data sets that are made available for scientists, for everyday users, anyone you want that to be. So I think, coming from the standards development organization, may be weird that I put this one up, but I'm going to refer to it. Actually, my first 15 slides, there is a possibility that we're actually going to add one on top of this. Hopefully, my last 4 slides will do away with this, okay? So keep this in mind and make sure that I don't add another standard. Citizen science. So this is, as I said, folks like you and me that go out and make observations. Typically, citizen science, when they observe, is very task-oriented. So before a group of folks go out and do something, there is a task that is created. That could be, let's imagine we're in Wales, and we say, okay, it's Sunday, sun is shining. Well, it doesn't happen that often in Wales, but okay. And we're going to go out and observe an invasive species in Wales, Japanese knotweed. That is the task. So we all go out into an area that has been predefined. We go out and try to observe that specific thing. So it's very task-oriented. Does it work, citizen science? It does work. So here's a group that does observations on biodiversity. It's called GBIF. You can read the numbers for yourself. So very impressive numbers, I believe, and that really means that it works. So folks do go out there, observe, and we can use that data. Now, when we do that and we try to use that data, it isn't always easy to use the observations in combination with other data sets that are out there that we want to use. The context in which these observations are made is important. It's crucial, actually. And so that'll be the first part of my presentation is making sure that we understand the context in which these things are done. Knowing that GBIF is just one of the many citizen observatories that are out there. There's hundreds, maybe thousands of these organizations that organize themselves and go out and do observations. That could be on biodiversity, could be on air quality, name a topic. Observing stars is another citizen science, just to name a couple. What you see here is that all define their own tasks and all define their own campaigns that they want to run, of course, using different formats, different organizations. Everything they do is the way they want to do it. There's very little organization that is associated with citizen science. So it's very ad hoc and very, let's try and do this. Makes it a bit more challenging if you want to reuse that data in combination with other data sets. That's the core of the presentation here today. And that is, how can we make that variety of those different data sets, how can we start using that in other data sets without too much human intervention? And that is, today, if you use citizen science data, there's a lot of manual tweaking, manual massaging that needs to be done for each data set that you would like to use in combination with another data set. You always have to put it through some green magic before you can use it. So there's a lot of tweaking, transforming that data into a format that is known to you so that you can start combining that. So there's a lot of manual man tasks that needs to happen before you can use that citizen data, which is a shame because that's where if we can easily integrate that data, then we would use it more often. And that's what we're looking at from an OGC perspective. Is there a way that we can standardize some of this? Now, if I go back to this one, there's this famous quote from someone in the citizen science when we say, okay, we're going to standardize this, so we're going to think in models and schemas, and someone stood up and said, I don't want any stinking schemas. I'll do whatever I want to do. So if we come up, or if we come from a standards development organization, it'll be a tough sell. Those organizations do whatever they want to do, and that's fine. So what we ideally, and if you remember the joke in my second slide, this is the potential for another standard, okay? We did this exercise. So ideally, if you standardize the work from the citizen, the environment in which you do your citizen science, and ultimately the sensor, if you combine that, then you can have observations that are comparable, that are interoperable. But it is utopian. I don't think it'll ever happen because it's the Wild West when it comes to citizen science. And that's fantastic. That's good. We shouldn't be trying to change that, I believe. But we did do the exercise. So once you have that citizen science data, how do I optimize this for discoverability? Simplify my data access, so to reduce that data massaging that needs to happen. What vocabularies do I use? So I was involved in a Horizon 2020 Citizens Observatory project 5 years ago. It was called Cobweb. That was trying to do research in citizen science in biodiversity monitoring. And so one of the things we did was on temperature and some very basic sensing things. And we noticed that just for temperature alone, there were 56 vocabularies. 56. I was hoping for one. That would be ideal. We found 56, which is ridiculous. And as we dived into it, it turned out that it was actually great project output. Let's define or create a vocabulary. That's the last thing you should do. Create yet another vocabulary. Okay, reuse what is out there, build on top of it. But if you want to create a new one, ask yourself that question 1,000 times. Should I really be doing this? Okay, don't. How can I reuse existing tools to get to that combination of citizen science? So from a standard organization, we looked at, okay, is there any base model that we can work off from? And so O&M, observations and measurements, is a model that is widely used in the sensing world. Even if you look at the IoT world or in remote sensing, O&M is widely used. So I say, let's use this as a base model. If you know O&M, then you recognize this image. Yet, even with standardized, it does allow you for various levels of freedom. So let me make that more specific. So on the top there, that's a depiction of Wales. Anyone from Wales here? No, okay, so you won't be able to recognize it then. So that's me on the left, and then as part of the task is, okay, let's go somewhere. Let's see if we can find some Japanese knotweed. And so off I go into the mountains, and I do 4 observations where I have my app with me. I used to have a smartphone. So I take my smartphone and I walk around, I have an app on it, and then I see Japanese, I want to take a picture, annotate it, whatever, and off I go. So I have 4 observations. Now, how do I persist? How do I look at these observations? There's various ways how you can do this in O&M. So first one would be is you map those points on a coverage. Perfectly legal, works fine. Alternatively, you can have it as part of a time series, which is also fine. Or you can have it as part of a curve. or in the end is where, you can have it as part of polygon. So there's various ways on how you can interpret and use that data depending on probably the use case. Multiple citizen observatories could, for that very same thing, say, okay, we'll go for a coverage, and someone else said, okay, I'll go for the curve. All valid. So what we did is we actually piloted the 3 methodologies that are on screen here. So you take either true O&M through time series, that was the second one, pure O&M with GML Cov, and then the third one was to use SWE common and derive from it. We noticed that this was somewhat of the traditional way of doing it. This is not the thinking outside of the box part. So that is, it works, but still interoperability between the data sets was difficult. If you want to read up, that's the bit.ly. In the end, this I highly recommended literature. Download it now and then read it tonight. I'm sure you'll sleep after 10 minutes. But it's super exciting, specifically the last 10 pages. So SWE for citizen science minus ER is what you need to remember in the bit.ly. So kudos to Ingo Simonis and Rom Atkinson for putting this together. Definitely recommended reading. So from a data user perspective, from what you want to do is we observe the Japanese knotweed. I just found Japanese knotweed. Okay, that's my observations, the 4 that I had. Now, I asked the system, find me all knotweed and buckwheat family occurrences in 2015 discovered by citizens in this area. Because maybe you can derive some additional information from that data set that makes a statement on the invasive species on Japanese knotweed and see how we can avoid some of the things that Japanese knotweed causes. So when you make that query, could be a temporal dimension, 2015, could be thematic, say the Japanese knotweed, or geographic here or in the location where we defined it. And if we look at the issues related to, and I'm going to exaggerate the issues a little bit just to make the point. So if you do the search terms on Japanese knotweed and you put this into a catalog, it's not always evident what search term you should use in order to get the data that you want. Sometimes you have to be very specific. I think we're all familiar with it. So the depiction that you see here is, you'll recognize it. This is an SDI out of the box like we know it here. The relationship between the resources. So if we do a campaign near Frankfurt, one data set could define Frankfurt as a point, and another one would define Frankfurt as a polygon. If you would then ask for, give me all the observations in Frankfurt, what happens with the ones with a point, the other ones with a polygon? Again, that needs that additional massaging of the data in order to compare and get valuable results. Metadata usage in the citizens' science, remember, these don't have a directive. They use whatever metadata if the metadata already exists. Is it the ISO profile? Is it by profile? Or any of the others? How do you query them? Is the search terms, are they there? Etc. And then querying, depending on the aggregation level. This is important in citizen science as lots of the data is aggregated on various levels, and that is to make sure that the individual is no longer recognizable. Just to check, have I passed 7 minutes? I have 3 left. My God, I was speaking slow. So where we want to go, and this is the future situation, that is thinking outside of the box, right? Are you ready? So what we do is we introduce new terms to the SDI. And that is, the first one is dimension. Dimension actually comes from the world of the data cubes, and more specifically the data cubes as the OGC and the W3C define them in the joint exercise of geospatial data on the web. If you haven't heard about this, look that up. Really super exciting things. That defined an RDF data cube where they have 2 specific elements. One's called a measure, the other one is called a dimension. So what you do here, And dimension is, so a measure is, okay, here's the amount of coffee that's sold in this place in 2015. The dimension is multiple of these occurrences so that you can ask the data cube, give me all the coffee sold in this place or in 2015 or in that year. So it's a data cube, multiple dimensions. So first thing you're going to do is, remember the context, this is trying to combine the citizens' data so that it requires less personal massaging, but more that the machines can do this. So what the machine will do is it actually interrogate the data cube, get the dimensions to understand what vocabularies to query. Remember my example on the temperatures. So if you have various of these observations, chances are big that they use various vocabularies to mean the same thing. So that's the first thing you're going to do is read the dimensions to understand what vocabularies to query. Then once you have it, you can query the catalog to get a URI template. So most of these services are accessible either through a RESTful service or a well-known web service where you can have the URI as a template and you can fill in the parts that you're looking for, right? Because you do not want to remember by hand all the various APIs from the various citizen science associations. So the only thing you need to do is to replace the variable part with what you're looking for. Once you get the vocabularies, or once you get the vocabularies, yes, then you can start how do they relate to each other. Those are known concepts in the linked data world. And once you have those, then you can start getting to the actual services that provide you access to the data, and then use HTTP content negotiation in order to get into the encoding that you want. This is a novel approach. We have prototyped this, where we can get it to work. Now it's a prototype. If you abstract from this, you could apply this not just for citizen science, but for any environment where you have a lot of veracity on data sets. And data sets, a lot of them, but none of them are the same. That this is typically something that you could use. In the OGC, we have started an initiative called the Ogc Naming Authority, where we do the same thing, but then for standards. So you have various standards. We each have them conformance classes, and the conformance class has a link to the URI where you can do the actual compliance test. We have developed that, and that is beyond the prototype. That will be shown actually next week in Southampton. And one more last sentence, and that is you can also apply it in, for instance, smart cities, where you have a whole bunch of information that is not related to each other, where you can use this extended SDI to do data lookup without too much manual massaging. Thank you.
Thank you very much.
Oh, questions?
Yes, we still have room for questions. Before we go to questions, I just want to ask, is Catherine from Ifremer now in the room? Okay, we have a bit more time for questions. So, anybody with questions?
Uh-oh, I bored them to death.
Alessandro, could you use the microphone?
And introduce yourself, please. Sorry.
Yeah, Alessandro Sarretta from the Institute of Marine Sciences. I worked in Inspire a bit more on the O&M specifications, and curious just if you have had a look at the guidance on the O&M, or if there's a relation of the model we try to include in Inspire data specification word and this future review.
I need to look into the engineering report, but I do not think that that was considered, as this was a specific exercise on the citizen science part, not so much on yeah. But I believe it would be very comparable to, I've seen presentation of Kathy Schleit on this, and so I know that that is compatible with the work that is done here. Is Kathy here? No. I've seen her earlier. Yeah.
Well, we would have heard her.
It's true.
I also have a question. Your experience with this citizen science communities is that they are organic. So how often is actually that does it happen that API structures are just change?
Yeah.
So how do you cope with that? So it's a very dynamic, not static environment.
Absolutely. We don't want any stinking schemas. So, however, it's the Wild West, but they are somewhat governed. And there is the Citizen Science Association. There's a European Citizen Science Association. There's the Australian Citizen Science Association. There's also one, the one in the United States is CSA. And so they all come together in the OGC. Of course, they don't want to agree on the APIs, and they want to change them as much as they want. But they do agree that there needs to be a common approach to it, without them having to change, or the freedom for them to change the API and then just register the API as part of a measure in the data cube. So that is something that they would like to do. Getting them to agree upon that as a group is more difficult. It's pushing rope.
Okay.
Or herding cats if you're more of a cat person.
Yeah, no opinion on that. Are there any more questions? Yeah, Franz.
How do you talked about
The microphone is coming to you.
Franz Daphner, my name. And my question is, you talked about the vocabularies and a lot of different ones, and you know when they talk about the same. How do you detect when they talk about the same, and who is doing this kind of mapping?
Yeah. So there is a registry for vocabularies. It's called, what is it, love dot something, where you can have the registries through linked data science. There is a high probability that they could be the same. Some of them need to be manually linked. Some of them you could be done, semi-automatically. But there is a way that they relate to each other. Yeah. And that only needs to happen once. That relationship needs to establish just once. Yeah.
Okay, are there any more questions? So, if there are no more questions, it will be from my side the final call for Catherine Satra-Lebris. No? Okay, that seems that she either missed the room, also missed to upload her presentation, and we would then jump directly to Carlo. Yeah, and the applause for Bart, of course.
Here. Anyway, I suppose it's working. It's just here. Okay. I need to introduce my.
Well, of course.
I don't
know you.
Okay. You know me. Okay, I'm Carlo Cipolloni from Italian Environmental Institute, Environment Protection Research Institute. Now I'm in charge of Inspire Technical Implementation in Italy and also Environment Information System in Italy. So we're talking about these second topics and nothing about nothing related to art, because the citizen side is something that we take in account, but is not official one.
That's true.
And the work is made, of course, with the support and collaboration of most of other regional agencies. So in fact, enforcing last year a new national law is reorganized the environmental information protection system and defining a new structure. So enforcing in this year, in January, we're establishing a new system, the National Environment Protection System, composed by the regional agency or province, autonomy province that we have, plus the central lab that's composed by an organization called ISPRA. It's not the ISPRA where is located GRC. And another very important thing that we said this law is say that the unique official technical reference to archive, collect, disseminate the environmental information is the environmental distributed information system called SINA-NET. SINA is the information system, NET is the network of all the apps that we have. What does mean that? That we have to organize a structure. So more or less we have a SINA infrastructure where we have the regional information system called SIRA. Sometimes this is combined with the regional agency, sometimes no. Sometimes provided by data by the regional agency and then publish that. So we have a very different kind of composition of actors. Mainly the actor is the regional agency, but sometimes also the region authority. And we are to organize the data. So we are in charge to provide data about air quality, water quality, nature conservation, space distribution, habitat, geology, contaminated sites. So we have a full of different topics in that. And we have a different approach to reorganize data. So what I presented here is how we try to reorganize the different kind of data flow and how we create a common layer using a first course Spire. The general approach is that we have the different silos that provide data. The first step is to harmonize this data ready in the Spire schema, the Spire model. So in some way we have an agreement to produce a common data. And then we have an harmonization of a spatial object, feature ID. So we create, we explain better that we create a common layer based on the spatial object D, permanent D. And then we provide this data in different format. Of course, we provide metadata. The web service, mainly based on GC standard, of course. I mean, it's the weather that we use. And also the link open data, because most of the community has already provide this linked open data. So we have also to harmonize the link open data as a layer. The infrastructure workflow is more or less is like that. We have the regional silos or system. In some cases, we have the repository, the database repository, and we have to collect this information in different situations for this different purposes. One of course, is the national report that we have to provide to a European Commission for some obligation or to a unit for environmental agency, but also we have to provide data for citizens, of course, and we have to consider in that when we publish the data for citizens, we have to in some way harmonize the complexity and give us a very simple feature to a simple layer to give the information. So this is more or less the workflow. But behind this workflow, we have a different kind of a composition of a data flow. So, why not working? Okay. The general data workflow, we have a regional database or national, depend. We harmonize that. We create an harmonized Spire database, and then we provide, of course, metadata for dataset, metadata for service. We publish the service. We manage the metadata in our catalog. And then we manage all using an ID, and a permanent ID. We have a permanent ID for metadata, but we want to create also permanent ID for the spatial object, for the feature. We go more in details. So the first case, the case 1A, is very simple. We have already a national database, so like a protection site or like a contaminated site. So in some way we have to collect this information. We harmonize, of course, rather the Spire. We create the Spire database, and we publish in different way. We can publish as on the fly or as a specific transformation layer, depend what is the complexity that we have behind the database. For example, for geology, like borehole or like simple geological unit, we have a national one that is quite complex. So we not want to reinvent or rebuild the database. We prefer to using the on-the-fly system. and then we provide the service, of course. But this is the very simple case. The more complex one is when we have the regional. The regional, in some case, provide directly the data harmonized in Inspire to ISPRA. ISPRA is the central lab. But in some case, they produce directly the metadata. They publish the metadata in their catalogs. So the data set metadata is published directly in the national catalog, but the data is collected at the national level to create a layer. It's a typically example of a groundwater database, where we have a regional database that they publish, but we in some way collect and create a common repository to create, also in this case, an inspired pseudo database on the fly or physically, and then we publish the data set and the service again, but in the same manner of the previous one. The case 3 of the case C of 1 is still more complex one, because we have some data that is more or less is similar. We have the database at the regional level, we harmonize at the national one, but in some case we have some data that is directly provided by the region in a standard way. So we have to integrate this data. In some case, we have to create an integrated service. To do that, we need to create a special object permanent identification domain, identification reference point. So in this case, the actor is very complex, because we have some service available in the region, some data that is available in the region that we archive at the national, in the national lab, and then we have to combine that. The last one regarding the data flow is related to the case 2. It's more complex situation. This is the typical case of air quality data. The region have the air quality data, not all the region. Sometimes the environmental agency have the data, so we have a different actor at the regional level that play a role. So most of them publish the metadata for data and service, but sometimes also provide the data to us, or sometimes provide the data directly to the commission. So we have to harmonize a very complex situation to create a common data set following this SPI, of course. We collect this and we create a repository where we have some layer inside the repository, but not all the data is achievable. If you look into the real-time monitoring air quality, we're talking about millions of data per day. And we have data each day, so it's impossible to archive in one system. Otherwise, we build a mega system. Okay. Also, in this case, we need the integration. How we create this integration? So, in Italy, in some way, we are lucky. Before we have a presentation that talking about the registry. In another, the commission make a presentation where presenting the registry, and in our case also Italy applied to using this registry. And we have also a catalog, a national catalog of public administration with the persistent identifier for each administration. So in some way we have already an administration code list, and we're using this one as a first part of our code. Of course, when we producing the metadata for datasets and service, inside the metadata, the metadata ID is something that is composed with this IPI reference number. But if you look into the spatial object, we have to create new rules in some way. We have the public administration identifier, we have a database identifier, and we have a feature identifier. So, in some way, we have create a rule to create a persistent identifier for each special object, And we're using this one to integrate in a system. In one way, we're using this as a linked or interlinked element inside a simple layer, like a view service, but it's simple feature layer, where we can interlink using the URI of a persistent element to interlink the object. In this way, we not need to create again. If it is available in the region, like Emilia-Romagna in this case, we just link the object that they have. We not create anything. Again, how we organize that? This is just to give you an overview of our national infrastructure. So we have a national geoportal that is managed by environmental minister. Behind this geoportal, we have a national catalog managed by Italia Digitale, the Italian agency for the Italian digital agency. They have also set up a national registry that's quite important to register all the namespace, all the persistent identifier. And then we have also set up a national dashboard and national client to monitoring, validate the service and the data set, and to, of course, display the data. And this is related to the ISPRA national protection system that we have to build. So in some way, we have the relation. Just to go to the conclusion. Some conclusion, further action. So we have, now we are in place to set up a regional board with all the regional information system regarding the environmental information system, and also all the environmental organizations that play a role in this way, because we explained before that we have a very complex board. We start to inspire, to produce inspire harmonization. So we starting to unify the database. We select some priority. In some way, we identify the protection side as a starting point, but we look into the habitat, to the industrial emission, especially for production facility, high quality, noise, et cetera, of course. And then we have set up a central registry to solve and manage the spatial object as a persistent identifier to harmonize the layer. So in some way, we're starting to set up a system, a local system to reorganize the object that we need to manage. That's it.
Thank you very much. Are there questions for Carlo? Yes.
Yep.
If you go
Bart.
back one slide, it
Yeah.
says you wanted to unify the distributed database.
One back.
So the second, it says start the inspire harmonization procedure to
Yeah.
unify the, why would you unify the distributed database?
Unify the distributed database in terms of create a common Inspire database. So we not create a unique database, but we create some unified layer that we use in the database, like a view. In some way, when we create a simple feature, we create a unique feature that take in account also the regional data. If you look into the simple feature, you can create a link with the URI to the national data set, the special object, so you not need to create again.
Franz.
How is your view? Who is publishing an Inspire compliant dataset? Your organization, all the regional as well, or just your national one? Because it's quite tricky. Because
No.
level you have
It's
sometimes more.
not tricky. Depend to the data. Depend to the data. In some case, when we're talking about we have a national database, there are some data that is in charge of my organization or to the environmental minister, like protection site. So the protection site is more or less is a polygon where some official designated area is defined. So this is defined by the environmental minister, but also in the case of some other data, we are in charge to produce data at the national level. So in this case, we publish the data. There are some other data that could be available at different level, like, for example, hydrography, we can have different details of hydrography. So in some way, the hydrography level for the WISE, it's provided by my organization. But if looking to a very detailed hydrography layer, we need to go to the regional level because they have more detailed data. And there are some other, like air quality, where the regional agency or the regional environmental system are in charge to publish. So in this case, I not need to publish again, but in some way I'm in charge to produce or to support the environment minister to produce the European regulation layer or report. So in this way I have to collect in some way this data.
Okay, thank you, Carlo. If there are no more burning questions, I would ask for a short applause for Carlo. And we would continue with Phil. There you are.
Is there water? Good afternoon. I'm Phil DiCola, and I'm very happy to have a chance to, thank you, to give you my presentation, which I think amply meets the theme of the meeting, which is thinking out of the box. In fact, I think it even might be a jack-in-the-box with respect to the theme. It's so far out of the box. But you can see from my title slide that I'm rephrasing the famous quote from Edward Deming, who is a management guru, who said, "You can't manage what you don't measure." So here's the positive framing. You can manage what you do measure. And I want to introduce to you this initiative called the International Photonics Advocacy Coalition for Future Environmental Sensing. And what you can see here is an image that illustrates, I think, some of what Daniel Calleja's great closing plenary message today talked about in terms of implementation. And there are challenges and opportunities for the Inspire directive going forward in light of both the applications at the end side and also the data streams on the front side. And here you can see, I think two things that you see here are well in hand. You have a digital elevation model from radar measurements from space overlaid with multispectral imagery, both of which we heard a bunch of today in this room. And then though you see remote sensing from aircraft, from satellites, from top of Mount Wilson here in Los Angeles, and then you see tall tower concentration measurements, and there's mobile measurements on the land and also in the water around LA, and they're part of a project called the Megacity Project, which is, bringing together all of this incredible sensing power in many, many cities around the world. And it's the kind of thing that I think is really a powerful opportunity and challenge for Inspire going forward. So this, the International Photonics Advocacy Coalition, it was something that was spearheaded by the Optical Society, but it's a global effort that is really getting partners. It was kicked off in March in Brussels as part of a European Commission co-hosted event. And the goals are to educate, advocate, and to collaborate about these capabilities that may be able to close gaps and fill gaps, meet needs for the environmental sensing community. And I like to think of it as an analogy with the translational medicine, for those of you who are familiar with that term and with that field, which basically is taking the latest and greatest from the research world of medicine and in an interdisciplinary way, trying to accelerate the movement of those success stories from the laboratory bench to patient care. And really here, we're taking the great R&D that's on the shelves that has yet to produce sensors, and we're working with the end users, in academia and in government and in the private sector, to connect up with those user needs and to see where there's a mapping between a capability that exists on the shelves
and an unmet need in observing. And the ultimate goal, of course, is that this information is going to be used to solve problems. It's an international effort. You can see there's quite a few Europeans, and there's Asian involvement, Australian involvement, South American involvement. These are just the people who are involved in the steering committee, but they represent communities of people that they are working with all around the world. So now I want to give a few examples of what I'm talking about, and it's not going to be covering the full breadth of resource management and environmental challenges. It's going to focus on the climate change example. And so I asked this question, why do we have a Paris Agreement? Well, the answer to that has to do with the fact that that these very careful measurements were the cause for concern. So you have the famous Keeling curve of the geometrically rising concentration of CO2 in the atmosphere, and the many different temperature records which show the global temperatures rising. And then there's evidence of the impacts from this warming already that we all are familiar with. And so it was evidence-based information that got the world together to put the UNFCCC process that led to the Paris Agreement. But that was not a foregone conclusion. I mean, in Copenhagen, there was a great hope that we would have an agreement there, and that failed for many reasons. We can talk about that offline, but ultimately, this was a picture I took from Lima, Peru, for COP20, and then the following year in COP21, it was an incredible event, and the French did an amazing job of hosting it and holding all of the different countries' hands and getting an agreement. And that was because the process was flipped around from a top-down treaty process to a more of an aspirational bottom-up process. And that's the same thing we're trying to do now. We rang the alarm bell with measurements, and now we want to make sure that the evidence-based information is used to guide us along the solution pathways for the countries who have pledges and are sincere about attaining them. And a nice example of that is this initiative that's spearheaded by the World Meteorological Organization and the UN Environment Program with this horrible name, but we'll not dwell on that. But it's a really exciting, again, translational medicine kind of activity, which is to say we have these great success stories of bringing atmospheric concentration measurements together with the normal data, the statistical data that's used to track emissions of greenhouse gases. And then what we're doing is finding where we have the ability today to improve our understanding of these fluxes of these greenhouse gases and work with the users who see the value proposition, and we build these end-to-end systems that take advantage of the data flow that INSPIRE Directive has led to and will continue to grow as more and more types of data are embraced by INSPIRE. And here are the objectives of IGUS. I'm going to give you a couple of examples of how we are building end-to-end solutions in this way. I'm going to show one example from national reporting of inventories, and then another example for, I think I have I have an example from the private sector in terms of looking at, people say all the time that methane, that natural gas is a bridge to a renewable energy future, but if the emissions coming from the supply chain of the methane are too great, then since methane is a much more powerful greenhouse gas than CO2, that proposition will fall on its face. So here's an example from Switzerland. They and the UK are the two countries that already use measurements and model analysis in part together with their bottom-up statistical data. And here you can see the Swiss have deployed these very advanced cavity ring-down sensors on tall towers to measure methane all around the country. And they combine that data in an inverse modeling approach. And what you see is that, well, the total that was originally estimated for methane emissions in this year from Switzerland was in pretty good agreement after you combine the atmospheric measurements with the statistical information. But the uncertainty dropped enormously so that we have a much better sense. And when you look at the prior statistical information, in respect to the final answer that you get, you see there's a big change in the distribution of those emissions. Turns out that while the total was in agreement with this analysis, the spatial distribution was very different. And this is really important if you're looking for fugitive emissions of methane and you're looking for opportunities to reduce from a given sector. You need to know in a spatial detail where the emissions are coming from. Here's another example of how advanced technology in optics and photonics can improve our ability to reduce methane emissions. Here is a pixel. This is a hotspot that was observed from space of methane concentration. Here you can see what's going on in that vicinity of California, and you can see there's a lot of oil, methane, natural gas, oil fields, and dairy activities which have a lot of methane from the waste management. And then when we used airborne capabilities and both at the facility level and then within the facility, we can zero in this particular case, this hotspot, this big source of methane was actually coming from the dairy activities, the waste management there. So this really is providing operators an ability to find the missing sources of these very powerful greenhouse gases. Here's an example, again, of advanced technology that can solve one of the really, really compelling problems in constraining the fossil fuel CO2, and our ability to separate it from the biological fluxes. How do you do that? That limits our ability to really get at the details of fossil fuel CO2 emissions around the planet. And the way we can do that is measuring the radiocarbon CO2, one where you have the ratio of this, because of the fact that in organic material, living material, you still have some of that around because it's incorporating what's naturally in the atmosphere, but fossil fuels are completely devoid of it. So that ratio is allowing us to make a comparison here, but the problem is we don't have enough of these analyses, and we need to have more, and it turns out that spectroscopic optical approaches are on the verge of allowing us to deploy these cost effectively without the need of particle accelerators to make the measurement. So these are a few examples, not broadly over the whole environmental spectrum of needs and applications, but focused on climate change. This is basically a summary of the points I just made in terms of the value of this, the ability to make more deployable, lower cost, smaller, lower power consumption capabilities. And then here's just a couple of other gee whiz kind of gadgets. These are we now have gigapixel multispectral imagers that can advance the kinds of land imagery that we've been hearing about today. These are LEDs, low cost, very stable LEDs for fluorometric measurements. On drones, you have quantum cascade lasers, which are able to be deployed very efficiently. As you can see, they're very small, low power, and they give us laser light in regions that help us detect all kinds of air quality and climate change species. You have high-powered lasers that can be used for three-dimensional mapping much more efficiently to get that very powerful information available. There's frequency combs for remote sensing. And then if we're ever going to be able to take advantage of CubeSats to really lower the cost of satellite monitoring, we're going to need these nanostructures that allow us to integrate electronic and optical capabilities in a single package, so that there's a group called ZARM at University of Bremen, and they are in partnership with my colleague and friend John Burroughs, who is building sensors, and they're developing these techniques that if you can have, again, small enough detector arrays that can give you the stability and signal to noise without big cooling systems, which wouldn't be deployable on such a tiny little satellite, and also having dispersive elements, optical dispersive elements that can fit in such a small package, we can really advance our ability of detecting and monitoring things from space, as the Copernicus program is wanting to do as it moves forward into the future. So this is the summary. again, photonics-based sensing has valuable applications for environmental monitoring. It does produce challenges of compatibility with the INSPIRE framework and key questions that must be addressed, how to overcome the challenges of making sure that we're able to characterize these measurements and the metadata is going to be able to fit within the INSPIRE ontology. And then EU policymakers, we're working with them already, and many of you in the audience might have interest in knowing more and getting involved if you're in the sensor game. And thank you very much for listening. I'm happy to entertain any questions, and here's a link that would tell you some more and how you can get involved. Thanks very much.
Thank you very much. Thank you very much, Phil, for showing
Thank
us
you.
the potential of photonic and optical approaches. Are there any questions from the audience? I had a question. Actually, you answered it partly on the last slide because I was not sure where do you see those approaches featuring in the data infrastructures. So we have data infrastructures for environmental data. So do you see them already featuring in there? So you mentioned some challenges.
The challenges I see, Christian, are when I went through and educated myself about the different objectives within INSPIRE, and I looked, for example, at atmospheric data, I was surprised not to see a lot of characterization of concentration measurements and those kinds of things in there. So I think, and I think that there's just a lot of other kinds of information that could be taken advantage of and that could flow through the INSPIRE data streams that are currently not accounted for and would require that. Now, I know that ICOS, which is the European Carbon Observing System, I know that they work very hard. Alex Vermeulen, who's in charge of their data systems, has told me that they're INSPIRE compliant. And but I think there's a lot of information that goes along with these, and they're making these kinds of measurements. And then the IGUS effort, which is an international effort, would like to take advantage of what INSPIRE has done because we're going to need to have some way of having interoperability over the whole globe, ultimately.
Yeah, I guess also this in situ data, access to in situ data is quite important for validation and ground testing.
Yeah, in fact, it's not. I go even further. It's not just validation of satellite measurements. I mean, the satellite measurements that we're making are necessary for to answer certain questions, but they're insufficient to answer just about any question. So we need that whole tiered suite, that whole array of measurements from the ground all the way up to space. We will always need that because, and it just depends on the question. We don't go in presupposing what the gadget is, what the measurement is that we need. We look at the requirements to answer an important societal question, and then we look at building a system with the different pieces from, like that tiered approach I showed for methane in Southern California. You know, there we required, pretty much the whole cake. But in some cases, that won't be needed.
Okay, thank you. Are there any more questions for Phil? No, if not, then thank you very much again.
Thank you.
And I would ask our last speaker of today, Halil. So we had a change of speakers as the speaker who was expected to come, Shemep Kos. I'm not sure if I pronounce it correctly, could not come, but happily you are able to replace, and we're looking forward for your presentation. Siri, could you? Well, if it's already open, could it be one of the presentations or? Okay.
Altta açıktı herhalde onda. Hello, my name is Halil Çeşme from Turkish Ministry of Environment and Urbanization. The purpose of my presentation is temporal change analysis performed by the Ministry of Environment and Urbanization. You can see the main topics of my presentation. Geographic data changes continuously in the course of time as everything does in the world. Present time only reflects the latest status of geographic data. In this case, it is not possible to see the former state of the data. Those temporal analyses cannot be performed. Nowadays, the way to reach more accurate results in a shorter time is to use appropriate and update technology. Studies on detection of land use and temporal change are completely carried out by using most recent remote sensing technique and GIS applications. By means of thousands of true orthophoto products generated in this project, it is now possible to perform the detailed spatio-temporal change analysis throughout the county and even at building detail. TGIS is a subdomain of GIS which deals with spatio-temporal change in data. Unlike GIS, which focuses on current up-to-date data sets, TGIS primarily keeps focus on multi-temporal data sets and trace of extract change in both graphic and attribute data. Thus, TGIS fits better for a dynamic world to monitor continuous changes. TGIS responds to questions such as where, when, at, what happened. TGIS may be utilized in many areas which seeks for spatio-temporal patterns, historical geography, physical geography, meteorology, urban planning, landscape, architecture, transportation, forestry cadastral systems, infrastructure, etc. Working area. I want to introduce example project which uses the GIS at the northern entrance of Ankara city. You can see materials and methods we use. Google Earth image or true orthophoto. You can see the tree orthophoto and geographic data production sites at Turkey. True orthophoto and geographical data production project performed by the Ministry of Environment and Urbanization aims to produce image-based maps for all built up urban areas and their surroundings. Study area covers approximately 55,000 square kilometers and acquisition with 10 centimeter. GST was completed between 2014 and 2016. Based on true orthophoto datasets, up-to-date urban building inventory of Turkey is produced. All outputs of this project are shared free of charge with public institutions, organizations, metropolitan municipalities, provincial and district municipalities. Based on true orthophoto image mosaics are shared by OGC complaint geographic data services. And by means of these orthophoto products, temporal analysis can be performed countrywide. You can see the final products. And benefits. I want to show you a short video about us and our project. Okay. You can see more detailed image about the project. We produce 10 centimeter GST through orthophoto of the whole city areas of Turkey, and we are regenerating the necessary areas with the UAV systems. You can see the evolution of the aerial imagery and GIS at Turkey from 20s to now. At the end, the importance of TGIS and need for multi-temporal image datasets are increasing. However, but spatial and temporal resolution of satellites platforms may be not for directing change at building scale, resulting reduced accuracy for temporal analysis and periodic collection of very high resolution of orthophoto and UAV imaging capabilities offer great changes for TGIS. Time dimension has made GIS more interesting, and use of TGIS will be inevitable soon. Thanks.
Thank you very much. Are there questions from the audience? So if not, for me it was a question. So thank you very much for presenting that, and I guess it's a very important contribution to spatial planning in Turkish communes. To what degree, or let's put the question differently, are Turkish communities right now already using this data?
To answer your question, my apartment present,
Okay.
Mr. Akınkısa.
Okay, thank you very much. Are there any more other questions? If not, then I would ask for a big applause for all the presenters and Halil.
Thank you.
And I would also ask for equally big applause for Cyril, our room assistant. And thank you very much for joining the session, and hope to see you at the conference. And in case Catherine is now in the room,